that's awkward. You're right.
So anyways, this is part 2 of machine learning fundamentals series that we're doing. The first one happened before spring break, but this one's going to be an intro to clustering algorithms.
All right. So, what are clustering algorithms? So, clustering algorithms are just a form of unsupervised learning. So, for those of you who don't know what unsupervised learning is, it's basically a way of taking in some uncategorized data and being able to kind of parse it into different groups. For example, supervised learning might be we have images of dogs and cats. The computer is told these are dogs and cats, and it learns to decipher the difference between dogs and cats. Unsupervised would be it has no idea what the images are. It just receives images and then it tries to find similarities between the images to decipher what that image itself actually is. So there's lots of applications for clustering. Some very common ones are search engines. For example, Google might group together similar objects that you looked up. Let's say you look up a baseball. It might like associate baseball with like baseball bats and baseball caps. Other things include biology. If you're given like plant statistics, let's say the kind of leaf, color of the leaf, the actual size, you can put that into like determine what kind of plant that is. And you can also cluster with marketing. Let's say you have a user base and you want to find consumers who are like very similar to each other. You can compare them with like each other users within that same cluster. So yeah, clustering algorithms have a lot of different traits. This is going to be a more technical workshop towards the second half, but just to get some terminology so you guys are exposed to it. Some common traits of clustering algorithms are hard clustering. So for example, in the first slide, we had images of dogs and cats. Knowing that a dog is 100% a dog, or just saying that image is a dog, is like hard clustering. Whereas soft clustering, you give it like a probability value or confidence value. So you might be like 50% sure that this image is a dog, or 40% sure that's a cat. Partitional clustering is basically carving up your space into parts. For example, here we have a 2D plane of some feature set. You can kind of carve it into 3 parts, the red, the black, the green. And it plays a lot into hard clustering because these have like a concrete label. And this hierarchical clustering, which is basically saying clusters themselves can be further clusterable. And that plays into soft clustering because you can have a point that belongs to like multiple different clusters. So there are a couple of types of hierarchical clustering. You don't have to worry about this too much. But just to get you guys exposed, because this is an introductory workshop, we got agglomerative clustering, bottom up. Basically, you find clusters that are very similar to each other. You can group them together and you can keep going. And once you have a singular cluster, you can choose the optimal number of clusters based on your results and like further divide it up. And there's top down, which is the same thing except in reverse. If you guys want to read more into that, we got references at the end.
So the first specific method of clustering we're going to talk about is k-means. Also feel free to grab.
Yeah, feel free to like eat pizza as we're going along.
So k-means is basically an iterative clustering method. So basically what it does is on every iteration it's adjusting the means of the clusters of the data in an attempt to sort of define a cluster by the mean of the data that surrounds it. So to just kind of jump into the algorithm here, basically the first step is we're going to randomly assign k centroids to the space, and these are going to be our initial clusters. So in the bottom left corner, we have 3 randomly assigned centroids. We picked out that we're going to have 3 specific clusters in this space, so they're just kind of randomly assigned on the left. And then k-means is going to alternate between an assignment step and an update step. So the first step is the assignment step. So basically what we're doing here is we're assigning each point of training data to the closest centroid. So based on our random initialization at first, we're going to pick the training points that minimize that expression, this argmin expression. Basically what an argmin is doing is you're picking the arguments that minimize that distance expression. So we're minimizing the squared distance to each centroid by measuring the distance of each point to all the centroids and picking the minimum one. And that's going to be the definition of our centroids. So in this photo, it's just a frame from the GIF we saw before. Based on the random initialization, you can see that all of the data points are closest to the blue cluster on the first iteration of the algorithm. Oh, and also we usually use Euclidean distance, L2 distance, to define how far away a point is from another point, but you can also use different distance metrics like Manhattan distance or anything that you think might be the best distance metric for your data. So then we go through to the update step where we're updating the position of each centroid for each cluster. So basically what that means is you're taking the points assigned to your cluster and you're calculating the mean of all of those points. So in this case we have 2 dimensions, so we're summing up both the dimensions, dividing by the number of points we have in that cluster, and moving the centroid to basically the middle of the data in your cluster. So this frame is on the first iteration, so basically the blue centroid is the only one that moves because it's the only point that has data assigned to it. So it basically just moves to the global mean, the mean of all the data. So then what we're going to do is we're going to repeat this assign, update, until we reach convergence, which means the centroids no longer move around, they sort of stay at the same mean. On the left, we have the objective function for k-means, which is basically what I was explaining before. You're minimizing the squared distance between all of the points and all of their clusters. So you can kind of see in the GIF how it's sort of stabilizing at the end there. So when we go to implement k-means, this is sort of the algorithm. It's just a different way of visualizing the algorithm and how we can implement it. So we're initializing our cluster centroids, and we're going to have the assignment step, the first line, and the update step is the second line, and we're going to repeat that until convergence. So we're going to go through every data point. We're going to assign all of the data points to a centroid by minimizing the distance from all the data points to their respective cluster, and then we're going to update the centroids by calculating the mean of each cluster. That's just another way to represent that. So when we talk about prediction, one of the main reasons we do clustering is so that we can take in a new test point and say, okay, I have this customer, for example, who has these traits. Which cluster would this customer fall into, for example? So once we're done training our k-means model, we take our test point and we just calculate the Euclidean distance or whichever distance metric we used of that test point to each of the centroids. We choose the minimum distance, and that's the cluster that our test point belongs to. So some characteristics of k-means. One thing that can kind of be a disadvantage in some cases is that there's a fixed number of clusters, right? So we have to determine the number of clusters we want before we actually start the algorithm. In most practical cases, this isn't super feasible, right? Because sometimes we can't plot the data so nicely like we did in that animation. Another trait is that it often produces clusters of uniform size, so it's good for data sets where you have an equal number of examples in each cluster. Another sort of disadvantage is that it's very sensitive. So depending on where you actually initialize the centroids, especially in a space that's not very linearly separable, the actual outcome can be very different. So for example, in that image that we have there, this data isn't linearly separable, right? But we will want to have clusters representing this sort of set here and the middle set here. But what k-means has done is it's very literally minimized the distance of each point to each cluster, and it's created this weird like divide between the two, which isn't necessarily desirable in all cases. And if we were to initialize those centroids at any other point, we could divide the data any other way. So sometimes it's not so meaningful, but it is very fast and easy to implement, and it is very widely used. So the next algorithm we're going to talk about is DP-means clustering. DP stands for Dirichlet process. I'm not going to get too much into that, but it's very similar to k-means, and I'm going to just sort of point out the algorithm and its like main differences from k-means. So it's going to kind of fade in as we go.
Yeah.
So basically what we're doing in DP-means is we're not actually choosing the number of clusters we have at first. We are initializing only one cluster. So all of the points will initially belong to the only cluster, which is represented as the global mean of the data, like the mean of all the data. So in that equation, basically the initial centroid is just the number of points is normalizing the sum of all of the data points, and that's your centroid at first. DP-means will have the assignment step just as k-means did, so we're assigning each point to the closest centroid. Obviously on the first iteration this is going to just be the one centroid, And usually we use Euclidean distance for this method as well. The update step is where it gets a little funky. So when you're updating your centroids, if the distance from the data point, at any given data point, is greater than this cluster penalty parameter represented by lambda here, we're going to add a new cluster. So basically what we're doing is, if by this cluster penalty parameter that we're choosing, we are going to add a new cluster if any data point is greater than that distance. So k goes to k plus 1, and then we set the centroid of that new cluster to be the data point that triggered this reaction, that was greater than this cluster penalty. Otherwise, we just place the point to the nearest cluster. And then we're going to find the new centroid as we did before. We're just going to take the average of all the points assigned to that cluster for each cluster. And then we're going to repeat again. We're going to do the same thing until the clusters no longer reassign when you're updating and assigning and updating. Yeah, so when we go to implement dp means, this is very similar to k-means in the implementation. So basically we have our initializing k equals 1, so we're starting off with k clusters, which is one big cluster, all your data points are in it, and the mean is the global mean, meaning the mean of all the data. This initializing cluster indicators is basically when we do hard clustering, so k-means and dp-means, as you've seen, are hard clustering algorithms. We're saying, okay, a data point is in a cluster or it is not. So we're initializing cluster indicators, so we're associating each point with the cluster number that it's in. That's what the cluster indicators mean. For every data point, we're going to initialize some indicator that tells us which cluster it's in. And then we're going to repeat the assignment step and the update step. For every data point, we're going to compute the distance for all the clusters, assign each point to a cluster. And then if we find that the minimum distance from any of the clusters is greater than our cluster penalty parameter, we're going to create a new cluster and have that data point be the centroid of that new cluster. Yeah, and then we're going to reassign the centroids. So to make this comparison a little more obvious, I put the objective functions for k-means and dp-means up here. So basically the goal of k-means at the top is just to minimize the squared distance of all the data points to all the clusters. In dp-means, basically what we're doing is that same objective function plus this cluster penalty. So the cluster penalty parameter is the lambda times k, which is the number of clusters. So yeah, it seems like a very simple addition to k-means. So the big advantage to dp-means is that the number of clusters isn't fixed, right? We start off with 1 and then we sort of keep adding until we find the correct number of clusters based on your cluster penalty parameter. And that parameter is sort of controlling the trade-off between the k-means objective, like minimizing the distances, versus how many clusters you want. So for when you're in your objective function, when you're choosing the cluster penalty parameter, if you want a small number of clusters, you would make that penalty really large, right? So that when you're trying to minimize this objective, then the algorithm sees, oh man, I'm going to get a huge penalty if I add another cluster here. And then prediction is the same as k-means, as with other clustering algorithms. And like I said, it seems like a simple addition to k-means, but it actually comes from a really intense derivation, which I'm not going to get into, unfortunately. It comes from Bayesian nonparametrics and Gaussian mixture models, which is fun stuff. And yeah, so basically it can minimize the number of clusters based on your cluster penalty, so which is advantageous in some cases.
All right, so now we're going to get into mean shift. So mean shift is a clustering algorithm kind of similar to k-means, but not exactly. So as you can see, this is a topology graph of various points in like 2D space. So how mean shift works is it starts by initializing centroids at every single training data point. So when this graph is initialized, you'll see that all these red dots, or the centroids, are dispersed throughout the graph because it's at the actual training points. We're going to initialize a kernel bandwidth. You can think of this as just like the radius around or the actual point. I'll get more into that later. And for every iteration, every centroid is repositioned to the mean of all training data points within its kernel bandwidth. So while in k-means, you're readjusting each centroid based on whether or not you're readjusting each centroid based on points that are labeled as it. Here we're readjusting centroids based on all the points that are within its radius. So a nice trait of this is that all the centroids are going to move towards points of higher density because you're adjusting each centroid to be like the average of all the points around you. If you have a cluster here and a point here, it's going to move this way because it's heavily weighted like in that direction of where the more population is at. So some characteristics of mean shift is, I said before, centroids converge to local high density areas, and the kernel bandwidth happens to be a hyperparameter. So hyperparameters, so basically choosing a number for the kernel bandwidth uses some pre-existing knowledge. For example, let's say we're dealing with images. If anyone's dealt with images, you guys know that RGB values are numbers between 0 and 255. So you can kind of use that number to guess like what kind of spherical value do you want, or like how closely related do colors have to be for it to be like a label. So these are just some examples. In epoch 1, 0, we just initialize all the centroids at each training point. The red lines is the actual kernel bandwidth around the centroid. As epochs go, the centroids actually converge to their points of to the local density maximums, and the red lines converge even more as you go on. So here's just some pseudocode of using mean shift. So we have some function update centroid. So you're going to take all the points, you're going to take a bandwidth, which is your hyperparameter, and the centroid you want to update. So you're going to find all the points within that centroid's radius, or within this red circle. You're going to iterate through all of those points, and you're just going to like sum them up and take the average. So this is a naive solution of it, but it works for most cases. So moving onwards, if a nice thing about mean shift is you can add probability to it. So this is a Gaussian kernel. Basically, it's just a bell curve, and I'm not going to get into the derivation of the math, but you're able to use this formula in order to like later on make your own probability density function based on your actual all of those centroids that you've had at the end of training cycle. So k is just going to be the kernel weight. So you pass in some point, it's going to be plotted here, and it's going to give you a value. And this is your formula. So a more practical implementation of mean shift, you're going to have your kernel function. And if you guys remember before, here we were just adding the weight and then adding like 1 for the average. We're kind of just multiplying the 1 by the weight and the point by the weight. And this just helps with doing further analysis later on. So this fancy function is just this, and there's lots of different kind of kernels. We don't have to worry about that. So yeah, mean shifts are soft clustering because you're able to assign probabilities to various points, because a point can remain within two separate, like, point can be within 2 radii, as we can see here. Another thing about mean shift is it's very slow. It works in n squared because we do initialize every centroid at every training point. And as you can see here, we're iterating through every centroid and then through every point. So it takes a very long time to run.
Okay, so moving on to our last specific method for today, we're going to talk about spectral clustering. So, like I said before with k-means and dp-means, the goal is to sort of create this cluster indicator matrix where we're assigning each point to a cluster via minimization of the objective. So you can sort of see the example cluster indicator matrix where we basically have, for each data point, we have one assigned to a cluster and not to any other clusters. So this turns out to be an NP-hard problem in k-means, which is why we're computing it iteratively. But it's proven that the k-means objective can be relaxed to a problem where the optimal solution can be computed via eigenvectors of a graph matrix, which I'm going to talk about right now. So the goal of spectral clustering is we're going to start off with a graph. So usually our data points just come as points, but basically what we're doing with spectral clustering is we're creating an undirected graph of all of our data points, and our goal is to sort of create a meaningful cut within the graph to represent similarities in that graph. So like, for example, in this graph, we have sort of very specific cuts of where our clusters are. So we are going through sort of like these edges to create this cluster of points that are similar in some meaningful way. So where this sort of comes from is actually from properties of graphs, where people have tried to create clusters in this way by using graph theories. So cut is one of them. So to sort of measure how we should split up these clusters, cutting the graph means sort of minimizing the weights on the edges that separate the clusters. So like those red edges are sort of symbolizing the edges that will minimize the amount of weight between the two clusters. So each of these edges will have some sort of weight indicating how important that node is to the other node, and we want to minimize that when we cut the graph. In the cut algorithm, there's some holes in it because, see, if you have a node that's sort of like off on its own, like right here, basically what the cut algorithm would do is it would create its own cluster for this one node, which is not really telling us anything about how similar the graph is. So that's why the more popular algorithm to use is normalized cut, which basically it's basically just the cut algorithm where we're minimizing those connections between the two clusters, but we're normalizing it by how many nodes are in that cluster, essentially. This is the NP-hard problem I'm talking about, but we can sort of relax this problem into not hard clustering, but rather one where we can solve it with eigenvectors, and I'll show you that right now. Oh, but before we do that, so I realized some of the stuff I might have been saying is kind of jargon for people who haven't heard of graphs, so just to go over a little graph terminology. Basically, we want to represent our data as an undirected graph, as opposed to a directed graph, which is on the right, because we have no flow of data, if that makes sense. So we're mostly just showing connectivity within a graph, within our data as sort of edges connecting our points with some weight that sort of indicates how important those connections are in that context. So actually creating the graph in a meaningful way is called a similarity graph, and there are a bunch of ways to do that. I'm going to talk about two of them, k-nearest neighbor and epsilon neighborhood, but basically what we're trying to do is create a graph of our data that's somewhat symbolic to how the data is represented, or how the groupings in the data work. So two examples. So on the left, the k-nearest neighborhood or nearest neighbor graph. This graph is basically just taking the 5 nearest neighbors to each point and connecting them. And then the one on the right is the epsilon neighborhood graph, which I think is a little bit of a better representation of how similar data is. You can kind of see how it's sort of capturing the local neighborhoods in the graph. And basically what it's doing is it's taking a ball of radius epsilon, so in this case it's 0.3, so it's taking every point within this radius is going to be connected. So a key element in actually computing the spectral clustering algorithm is finding the Laplacian matrix of the graph. So to do that, we're going to need 3 different things. We're going to need the adjacency matrix, weight matrix, and degree matrix of that graph we just made. So just to quickly go over what those mean, an adjacency matrix is basically a representation of how your data or how your graph is connected. So in this case on the left, basically we're indicating that 2 nodes are connected with a 1. It's either binary 1 or 0, since these edges are unweighted. They have no weight. So here we can see that node 4 is connected to node 1, 4 is connected to 2, 4 is connected to 3. And then we also do it on the other way, so this is a symmetric matrix, right? Because we also have to say that, well, node 1 is connected to node 4, node 2 is connected to node 4, etc. And so on the right, all of the nodes are connected to each other. So there's all 1s except for the diagonal, because none of the nodes are directly connected to themselves. So what we're going to be using to compute the Laplacian matrix is a weighted adjacency matrix, which instead of binary, we actually take the weights of the edges into account. So basically what we're saying is that we denote that 2 two nodes are connected via their weight. So for example, node 0 is connected to node 1 with a weight of 2, and etc. So the degree matrix is kind of the sum of the adjacency matrix in a sense. It's basically denoting for each node how much weight is on that node. So we're taking the sum of all of the weights connected to node 0, 1, 2, 3, 4, and just placing them on the diagonal. So for node 0, there's a value of 5 because it's connected to nodes 1 and 2 with weights 2 and 3, which add to 5. So then we want to compute the unnormalized graph Laplacian. So there are actually many types of graph Laplacians, but I'm going to be talking about the unnormalized one. There's also normalized graph Laplacians and normalized spectral clustering. But basically, to compute the unnormalized graph Laplacian, we're going to take the adjacency matrix and subtract it from the degree matrix. So when we get the Laplacian matrix, all of the values on the diagonal are going to represent all of the weights on each node. And then all the other values are going to be negative based on how they're weighted. So there's a whole field of research that investigates Laplacian matrices and why they're important and why they represent similarity called spectral graph theory. I'm not going to go too far into spectral graph theory, but I can say that the Laplacian matrix is a very good representation, especially on a similarity graph of how your data is connected. And that's what we're looking for in spectral clustering, right? Because we want to define the clusters of your data based on how they're connected. So another thing I'm going to brush over a little bit, but we're also going to use eigenvectors. And basically what these eigenvectors do is uncover the connectivity of the graph. So we're taking the eigenvectors of the Laplacian matrix that we just calculated. So the importance of the eigenvectors here is that when you have the 0th eigenvalue of your matrix, the eigenvectors associated with that eigenvalue are going to reflect the connectivity of your graph for the k clusters that you've defined. That being said, so basically what we're saying, the spectrum in the spectral clustering name refers to the actual eigenspace of the graph Laplacian. So we're taking these eigenvectors, and in this space, we're sort of trying to define how that graph is connected in a mathematical way. A bit of a less important point, but for two similar graphs, the Laplacian matrices and eigenvectors are going to be similar, or the same. So, yeah, this is going to sort of help us determine how a graph is connected. So, here's sort of the algorithm. So, I kind of went through it a little bit already, but to have it all on one slide, basically what we're going to do first is we're going to take all of our data and we're going to find some meaningful representation of it as an undirected graph. So we're going to connect those points in some meaningful way via k-nearest neighbor or via epsilon neighborhood, whatever you find most suited. And then we're going to compute the graph Laplacian. In this case, it's the unnormalized graph Laplacian. There's also normalized spectral clustering, like I said. And then, so we're going to take the lowest k eigenvectors. So this algorithm depends on k, right? So you actually need a fixed number k that you want to cluster your data into. Yeah, so basically we're going to take the first k eigenvectors associated with the first eigenvalue of the Laplacian matrix. An important point here is that when you sort of take these eigenvectors, what you're doing is sort of reducing the dimensionality of the problem. And I'll get into that in a second. So what we're going to do is we're going to put these eigenvectors into a matrix. So once we have our eigenvectors, we're going to place them, each column, into a matrix. So you can kind of think of it as each eigenvector is going to represent sort of a feature of the graph. So like when you have a data matrix, you have like an n by d feature matrix, where every column is its own feature. So in this case, we're going to use the eigenvectors as sort of like a feature space in this like new similarity space that we've defined by taking the eigenvectors of the Laplacian, if that makes sense. So then, since going back to that analogy of like a data matrix, we're going to have for every data point this matrix of eigenvectors that represent our features. So we're going to take each row of that for every data point, and we're going to do k-means on it. So yeah, like I said, acts similarly to dimensionality reduction, often creates a more meaningful solution because we've taken the similarity of the points into account already. So this is just another way of looking at the algorithm. I basically just said all this. So, but yeah. So some characteristics of spectrum clustering. As you can see, it performs very differently than k-means does. Again, since we've done the similarity graph, we've taken into account the similarities of the data beforehand. What we can see is that it sort of is better at getting the underlying structure of the data. So on the right side, when you have this mini batch k-means, which does something similar to what I mentioned before, how it just kind of randomly like splits the data linearly somehow. Whereas spectral clustering actually gets the two sections of the data very clearly. One disadvantage is that it's slow. I mean, you can picture like a huge data matrix. If you have a lot of samples, then computing the eigenvectors of that matrix is going to be slow. And it also has a fixed number of clusters. But it is advantageous because we get a better representation of our data.
All right, so just as a show of hands, who here knows Python? If not, I'm still going to walk you guys through it. But all right, cool. So we have a few coding examples. So just for now, we're going to show you guys this workshop. So on GitHub, I'm going to pull up the link in case you guys want it on your local machine. Just give me a second. BUMIC. So if you guys go on GitHub, go to BUMIC and go to Deep Learning Series. We have all this code here under Intro to Clustering Algorithms. So it's nice knowing, hearing about different clustering algorithms, but the great part about them is they're really easy to implement and really nice. So just to show you guys some simple Python code, to start off with, I'm just going to initialize some data points. So you don't have to worry too much about this, but we're setting a seed. We have some points, make yada 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 yada, and just plotting it here. So for our first algorithm, we're going to use k-means. So if you guys recall, k-means, it's going to find all the points closest, whichever centroid a point is close to, it's going to get that classification. After it gets that classification, for every centroid, it's going to take all the points labeled as it, it's going to average them out, and it's going to reposition the centroid accordingly. So to start off with, the only function we really need to pay attention to is this fit function. So we're going to initialize our centroids. It's just going to be random from values -5 to 10, just because our points are kind of within that range-ish. Should actually change the range, but we'll do that later. After we initialize them, it's going to have size, k, and features. So k is, once again, that hyperparameter we specify. And number of features is just going to be 2 in this case because it's a 2D graph. All right, so next function. So we're going to stop iterating once the centroids aren't moving, if that makes sense. So that's all this while loop is doing. So while not equal the previous centroid batch versus the current one, we're going to keep going. So we want to keep going until the centroids actually converge. So we're just going to copy, we're going to store what the centroids currently are, some shape statistics. So next centroid is just going to be a bunch of zeros, numbers of points per centroid, also zeros. For point in self.train, we're going to classify the label. So the classification, if I go up here, blah, is just going to be like a Euclidean distance. So np.lineage.norm. That is NumPy. NumPy is just a matrix library for Python. It just finds the Euclidean distance between two vectors. So we find the Euclidean distance, and np.argmin is going to find the shortest number within an array. So just to show you guys what that looks like. Can you guys see this? Or yeah, okay. So let's say I have some array, just 1, 2, 3, np.argmin. It's going to return the index 0 because 1 is in the 0th index. If I made, just to prove, 2, 1, 3. going to print out 1 because that's where the smallest index is. So this is just returning the shortest distance, which is how we're kind of labeling stuff. So after we do that, we're going to just add 1 to the number of centroids because we're finding the average, so we want to keep track of which centroid has which point and whatnot. So this is just going to be like our denominator in the actual point itself. So after we've iterated through every point and labeled them, we're going to go through the centroids and we're just going to add what their the average was. So we're going to reposition the centroids. So next centroids of I is just going to divide equal number of points. So next centroids was the actual summation of the points. We just divided. The reason why I have this if statement is because you can't divide by 0. It could be the case that we initialize a centroid outside, let's say no point is near it. So that could give errors. After that, we're just going to, that's the whole fitting function. So what that kind of looks like is we have these yellow points, which are the centroids. You'll notice that for each epoch, they start to move towards places of higher density. Yellow probably wasn't best color, but yeah. So once it hits epoch 6, it stops. So one thing in practice that's nice to do is you want to run k-means in batches. So because the centroids are randomly initialized, as I said before, they can be in a place that's not near any points. So that's why I made a best fit function. Basically, it's going to run fit several times, and it's going to calculate the squared error of each trial. And it's going to use the trial that has the smallest squared error. So I have that squared error function defined up here. And yeah, so squared error is just going to be the distance between a point and its label, or the centroid and whatever that point is. Now for mean shift, the code is pretty identical, except we have a Gaussian kernel, as mentioned before. So in this case, I actually wrote Euclidean distance instead of just having it here. So yeah. And yeah, the only difference is mean shift, once again, is an n squared function. So because it is n squared, we're going to iterate. It's going to be slower. But yeah, we iterate through every point in every centroid. And we're going to have as many points as we do centroids because we initialize the centroid at each point. We're going to find the distance between them. And we're only going to use the points that are within the radius of the centroids. For example, in this red line. So it's going to take all of those. It's going to pass it to our Gaussian kernel, which is just that bell curve shaped, if you guys recall. That's going to output a weight, and we're just going to sum up all those weights and all of the weights times the actual point. That just scales the points down. We're going to find the average of all that, and we're just going to reposition the points accordingly. So on the same data set, you'll notice that the centroids have a lot more epochs. So k-means in this case only had 6 epochs. Whereas mean shift, it didn't, I had to stop it because it was just going. Because once again, it is a slower algorithm, but these classes are a little better. Yeah, also just to point out, I specified the bandwidth here, and I had specified the actual k for k-means here. So we have this centroid that's kind of in an awkward spot. So some nice things you can do with these clustering algorithms is you can do stuff like image segmentation. So an image is just a 3D space of a bunch of numbers: red, green, RGB, blue. So for example, let's say I input some image of a sheep. You can then just do some k-means clustering and pick out how many colors you guys want from that. So if anyone's interested, I'm going to do this live, just show you guys it's not too hard to put together. So I'm going to open up a new Python file. The only thing I'm going to copy over is this little clump of code. So yeah, all this does is it's going to basically just load in the image locally, and we're going to show it. So I'm going to make some class image segmentation. So some things that we want the k value because we want to know how many centroids we want to plot. I'll just let everyone take a second to open up on Jupyter Notebook if you haven't done so already. Yeah. So yeah, we have k, and I'm actually going to pull the actual image. So I'm going to take the image, I'm just going to reshape it what this line of code is doing right here is image.shape is just going to give the shape of the array, if you guys haven't used NumPy before. So I'm just getting the number of x pixels times the number of y pixels, which is like the total number of pixels in the matrix. I'm going to take this image and I'm going to reshape it such that we have just the number of pixels and 3. So 3 because it's an RGB value. So if I were to, for example, print out the actual shape of image, you guys will notice it has 3 at the end because the last value is going to be just the RGB. So yeah, so we have the channels, which is 3, and now we're going to add some other stuff. So let's start off with our fit function. So fit is going to initialize some centroids. Actually, I'll locally initialize it. So centroids, we're just going to randomly add k centroids around the graph, the space. So you can do that through np_random.randint. This is just going to return a random number within some range of 0 to 256, because the maximum number you can have is 255. You can have negatives. You can also specify the actual shape. So this shape in this case is going to be just the number self.k and 3, because the centroid once again is just a point in this like vectorized image space. So after we have the centroids, I'm going to add that while function. So while not. I'm also going to define previous centroids equals to 0 to equal just an empty array. So while these arrays aren't true, which means they haven't converged yet, we're going to do some code. So for each iteration, we're going to just find we're going to find the labels of like each point. So I have to have a label function. So I'm just going to call it def classify. So this is just going to take some point and some centroid, for example. Actually, yeah, I'll just leave this out. So np.argmin list comprehension. I'm just going to find the Euclidean distance between the point and every centroid to find which is the closest centroid. So if you guys recall, I can use np.linknowledge.norm and just subtract that from centroid. I'm just going to return this. So this is going to give us the index within self.centroids of the closest centroid to the actual point. Now, after I do that, I'm going to say label equals, actually got to iterate through the points, which I haven't done yet. So for point in self.image. So this is going to be just size of 3 array, like 1/5, like this number right here. Because keep in mind we reshaped it. So for each point, I want to find the label of that point. So label is going to equal the classification of it. We classify the point. After we classify the point, we want to then just add that. So I have to make some other metrics. We want to find the sum of everything. So point sum is going to equal so we're just going to find self.num of pixels, actually just k. So this is going to be, this is how we're keeping track of which point is where and where we're adding it to. It will make more sense with type code because that was really English, but yeah. So self.k 3. So we're just adding all the points to like this vector according to corresponding index, and num of points in centroid. So we're going to have okay. So point sum of that label. We're just going to add that point onto it. Num of points in centroid, just gonna add one. Yeah, we're just gonna iterate through that. Going to add that inside of this while loop. Equals self.centroids.copy. Yeah, the reason why I'm doing this is because we want to keep track of the previous centroids. So at the beginning of the while loop, we're going to resort the centroids and then we're going to update it. Once again, if previous centroid, this line, equals centroid before we ran the while loop, then that means it's converged, which is going to break this whole thing. All right, so after we do that, we're just going to iterate. We're going to update the actual centroids. So for I in range length of self.centroids, we're going to say self.centroids of I is just going to equal point sum I divided by num points. This is just finding the average. This is in centroid. So we're going to reset each centroid to the average of like the points, and yeah. So we're going to do that, and this while loop's going to run. So just to recap what we wrote so far, we're going to pass in an image, some k, number of pixels, and yada yada yada. We're going to have a while loop. When it converges, it's going to break. So now I'm just going to have a function that shows it. Segment, and I'm just going to pass this in for convenience. So I'm just going to store the shape. We're going to create a blank image. Now for x in range, we're basically now just going to reassign every pixel in the blank image to the classification that that pixel would have been. So for x in range of the length of, I can just actually delete that. For y in range of the length of original image of 0, I'm going to say blank image x of y equals, first we're going to find the label. We're going to classify that pixel of which we are clustering. After we find that, we're just going to say self.centroids of that label. Okay, and now we're just going to do pot.imshow. This is just going to show the blank image. Pot.show. I think that's about it. So now I'm just going to debug whatever live coding errors I got. So segmentor k-means equals image segmentation. So we have to pass in k. So we have this picture of a sheep. Someone give me a number for k. It could be anything.
12.
Maybe not that high. All right. Did I hear 4? I heard 4. All right, cool. So 4. We're passing the image. K-means fit. Yeah, probably gonna have to give me a second to finish debugging this. So centroid's not defined, yada yada yada. Okay, so just give it a second, and it's gonna take a little more than a second actually. But yeah, so that's pretty much all there is to it. You just 3D space, same thing as a 2D graph. You just kind of abstractify it. The math holds the same. I forgot that bit right here. Every dot zeros of shape. So that's good because that means it got to the end. I just had that little error. Yeah, So as this loads, does anyone have any other questions about workshop or clustering algorithms or whatnot? If not, yeah. Oh no. Required argument shape position one. Okay. I think. Oh, and very wait, that's good. As type int. All right, cool. Because I've had that error many times, so I know just like that what it is, or maybe not. Dot. Oh, I forgot to add the if statement. If you recall, I said you can't divide by 0 because it could be the case that centroid is not like close to a point. So this should be, if that's not equal to 0, then we're going to do this. Yeah. Okay, can't imagine.
I guess I do have a question about clustering.
Yeah.
Since clustering is like unsupervised and there's no train test split, like how sensitive is it to like introduction of new data? Like if you were to do like how sensitive is it to like introduction of new data? Because you're doing clustering on like pre-existing data.
Could you restate your question one more time?
Yeah, like by new data, do you mean like other training data?
Other training data or like test data based on like what you found to be in the clusters.
Yeah. Well, as far as like test data goes, I mean, you're not actually going to add that to your cluster distribution, so it's not going to really affect that. But as for training data, it actually depends on the algorithm you're using. But like for k-means, for example, if you add like a training data point that's like way out there, it could really adjust the centroid position. Yeah. So they're sensitive. They're even k-means is sensitive to like the order in which you traverse the data, right? Because the way the centroids adjust depends on how you go through it. Oh, nice.
But yeah. So sheep. Anyone want to give a different number for a k? 7. See. Oh, different image. Yeah. So I can take an image of the class actually. It's going to take a second. Yeah, I have. So the ones I have on hand, I can't really see. I'm like half blind. Yeah. All right. Let me open this up in Python. It's so small my screen. That's why. I think this is here. Open. So, I mean, unless you guys have a different image you want me to like try out. These are a couple of things I had. This one? All right. And how many colors? Because it's a lot of colors. So, I think I called it. 25. All right. It's going to take a second. I heard 24. I'll try 24. Sorry, dude. Let me just make sure that was the right name. That's not the right. Feeds.jpg. All right. I forgot to add 24 here. But yeah, so doing this with mean shift with a good enough window, that I'm not going to debug because that just takes, I'm not going to do because it takes way too much time to actually run. It kind of like smooths the image over. So if you guys get a chance, you should look at those. It looks kind of, it's nice. Yeah, I don't know how long this is going to take. It should take like probably 4 times as long as the other one because 4 more Ks. 3 more Ks. So. Yeah. But yeah, I'm gonna grab slice speed. Oh my god. Oh, okay.
Oh, it's going.
So you can see if it.
Yeah, my stomach was pushing me for food.
It'll be a surprise when it comes out.
It's gonna take a second.
Yeah.
I could scale down the image to make it a little faster. That might actually be better. What's an aspect? This is what? This is 4 to 5. So 4 to 5. I don't know, 90. That's not the same aspect ratio. I'm just
Okay.
yeah.
That's okay.
I feel kind of want to just let her.
Wait.
Oh. Ooh.
Oh,
Yeah.
okay.
Yeah. So yeah. I mean they're still there because we had a high K.
Should you decrease it to like
Yeah.
less than the number of colors you want?
Oh yeah, it's gonna be like you're gonna have brown, but you'll be able to make out the shapes. So just show you guys. I have to give a second. Wait, did I change this? I did. Move back to the previous resolution. Projecting music intensifies.
Does it go faster with more clusters?
No, so the more clusters you add, it slows it down linearly for k-means. One speed up I could do is I could put this in parallel because it's really easy to parallelize stuff. I just didn't do that for a live demo because I didn't write it when I originally wrote the code. But yeah. So for k of 3, once again, it's kind of brown because it's like finding the average, and brown's kind of like an average number. So yeah. So now you guys can go home, just look at this, and hopefully be able to implement just nice clustering algorithms. Thanks, guys.